In the previous video, we carried out point-to-point communication. This is the 12th video, Avoiding Deadlock Problems. In this video, we'll first introduce a typical deadlock problem, and then run a solution that allows us to avoid deadlocks by swapping the sending and receiving functions so as to make them asymmetrical. A common problem we face is that of the deadlock. This is a situation where two or more processes block each other and wait for the other to perform a certain action that serves to another, and vice versa. The MPI-4PY module doesn't provide any specific functionality to resolve this, but only some measures, which the developer must follow to avoid problems of deadlock. Let's first analyze the following Python code, which will introduce a typical deadlock problem. We have two processes, rank equal to 1 and rank equal to 5, that communicate with each other and both have the data sender and data receiver functionality. If we try to run this program, we note that none of the two processes are able to respond. Both prepare to receive a message from the other and get stuck there. This happens because the function MPI com.receive as well as the com.send MPI blocks them. It means that the calling process waits for their completion. As for the com.send MPI, the completion occurs when the data has been sent and may be overwritten without modifying the message. The completion of the com.receive MPI instead is when the data has been received and can be used. To solve the problem, the first idea that occurs is to invert the com.receive MPI with the com.send MPI in this way. This solution, however, even if correct from the logical point of view, not always ensures the avoidance of a deadlock. Since the communication is carried out through a buffer, where the com.send MPI copies the data to be sent, the program runs smoothly only if this buffer is able to hold them all. Otherwise, there is a deadlock. The sender cannot finish sending data because the buffer is committed, and the receiver cannot receive data as it's blocked by a com.send MPI, which is not yet complete. At this point, the solution that allows us to avoid deadlocks is used to swap the sending and receiving functions so as to make them asymmetrical in this manner. Now let's run this code to see the output. Enter this command. Let us type the print statement to see how it works. Finally, we get the correct output. The solution to the deadlock is not only solution. There is, for example, a particular function that unifies the single call that sends a message to a given process and receives another message that comes from another process. This function is called send-receive. As you can see, the required parameters are the same as the com.send MPI and the com.receive function MPI. Also, in this case, the function blocks, but compared to the two already seen previously, it offers the advantage of leaving the communication subsystem responsible for checking the dependencies between sending and receiving, thus avoiding the deadlock. In this way, the code of the previous example becomes as shown. Awesome! So we saw how to avoid the deadlock problem. In the next video, we'll see how to use broadcast for collective communication.